Опять вышли из постановочного просмотра.
Что?
А, все нормально, да?
Там заливка шарит, там кошечка. Вот она.
Ну, не может быть.
Оно просто будет текст.
А?
Должен быть какой-то текст, не будет видно.
Сейчас скажу, думаю, ничего. Хорошо.
Мы клавиатуру вот эту вытащили и нажали F11.
Да?
А как клавиатуру вытащить, сейчас непонятно.
Может, все-таки попробовать через Android открыть? Вчера получалось.
Давайте через Android. О, обычный режим.
Да, надо зажать. Обычно.
А Zoom, кстати, транслируется сейчас уже?
Нет, там просто YouTube ссылка.
А на Zoom нет, только по YouTube.
Все вышло.
Но заливка все равно осталась. Что он хочет заливать?
Может, просто выйти и перезапустить.
Мне кажется, это не так он что?
О, еще.
Ну все, теперь нормально. Вот я думаю, так хорошо будет. Все.
Спасибо.
Да.
Dear colleagues, we are starting today's session. The first talk today is Shuai Guo. I am sorry if I wrong in your family or name. And report about Virasoro constraints and the polynomial recursion. Please.
Thank you for the introduction. Thank the organizer for the invitation and for all the support during this visit. So today I want to talk about the result constraint and the polynomial recursion. This is based on a joint work with Qingsheng Zhang.
Maybe you can use it.
I can use this.
I remember it. I think it should have been on full screen mode.
Maybe I can try to. Ah.
Сейчас. Еще какие-то проблемы?
Не, он перестал
Перестал
листать.
листать.
То есть, может, как-то так вот
Перестать перестал.
Да, по-моему, в режим презентации, видать, не листает.
Ну вот.
Режим. В этом режиме листает.
Okay. So because the result constraint, I considered all the from the so-called enumerative geometry. So I will first introduce some axiomatic theory for the enumerative geometry. So usually we will have underlying we call the cold field theory, which was introduced by Zhang. So it is start from a vector space with a non-degenerate symmetric bilinear form eta. And then it consists of a set of maps. So the maps is it will eat n vectors of V, and it will output some cohomology class in the white space of curves emitting back. So this was already introduced in Shuai Guo, so I will just omit this. And this space is just consists of some curves, stable curves. Okay, so the point is, usually we do not consider the origin of Coulomb field theory. We usually consider what we call the shifted Coulomb field theory. That is, saying that we have some fixed vector tau, we can consider it as a coordinate near the origin, and then we define this shifted Coulomb field theory, this omega tau. So one can check that this, if omega is a property, then omega tau will be also a property. So it satisfies all the extent. I omitted here, but I think it also was introduced in Shuai Guo's. So it's saying that it satisfies some properties that is invariant under the SN action, and it's compatible with the Boolean map. Okay, so this is the coef T. And also, we have something we need to introduce is the so-called Frobenius manifold structure, because we consider this coef shifted coef T. That means this tau is this coef T depends on the coordinate tau. So this will also define the Frobenius manifold structure. The Frobenius manifold is just defined by this multiplication defined here, the quantum product. And because this quantum product depends on tau, so this will gives in fact a family of quantum product near this origin. And also we need to consider the fundamental solution of the following equation, what we call the quantum differential equation. Because here we not only consider the Coulomb field theory, but also we want to consider the universal geometry associated with it. The universal geometry will always define something we call the descendant. So the descendant will be related to the Coulomb field theory by this S matrix. So this is because the solution is sometimes it's not unique, so we call it S calibration. So it's the choice of S matrix. So the theory satisfies all.
What do you mean by generalized?
Sorry?
What do you mean by generalized?
Oh, because in here our Frobenius manifold may not have a flat unit. Okay, so the theory we considered including the following, like the Broomington theory, the FGRW theory, also the gauge-linear signal model introduced by Fan-Jack-Ran, also some theory defined by topological recursion, some matrix model also satisfy all this axiomatic theory. So we just start from the theory satisfy all this axiom, and then we do some computation. Okay, so then we introduce the generating series for this given unity geometry. So first we have the ancestor free energy, which is the generating function for the Coulomb field theory. So you have some input. This S is the coordinate of this free energy, you can think of it as. And then you can define this generating function. And then we also have some what we call the descendant partition function. So the descendant, so because here we do not we do not know what exactly the inertial geometry is, but in fact for each each theory it is correspond to a given S collaboration. So we can just define it just by this S. So given this S, we can define the two-point function W, and we can define the descendant just by this. So this was proved by Constantine Manin which connects the descendant ancestor in Grom-Witten. But now in fact the proof can be generalized to other series like W series or BGSC model. So we just use this as a definition of this descendant. And for given theory, once we know the S matrix, then we can have this descendant. And the descendant.
What is this W called?
W is a two-point function defined by S. It's to be precise, it's like W. W has two variables. W is equal to SZ times S star Z or W over Z plus W, something like that. So it's totally determined by S. And the relation between D and A is, in fact, it's just a coordinate transformation. It's S to T. Only except for the unstable part. The unstable part includes the genes 1 with no marking and the genes 0 with 1 or 2 marking case. Okay, then we first consider a theory with a flat unit. So later we will consider a theory without flat unit, but now we first consider the theory with a flat unit. So first, the unit, we always require a unit for the quantum product, means that because it's a product, so means there exists an element we call 1, it's the unit of the product. And then we call it flat if it satisfies this property. And this means it becomes the unit of the coil T. But we will have some examples that does not satisfy this. Right now, we first consider this case. And we also need some condition. First is we call the homogeneous condition, means that there exists a Euler vector field. So the Euler vector field has some data here. So we will see this data are also some basic data for the theory. So which are related to the so-called grading operator. The grading operator will be just, for example, in Grom-Witten theory, it's just the degree of the homology class. Then we will have some operator here called rho, which is related to, like in Grom-Witten, it's just the first train class. And we will have also an important constant called delta. So this delta is called the conformal dimension of this coil T. And we require this coil T satisfy this homogeneous condition. So also the theory we considered as the Grom-Witten theory, FGRW theory are all satisfy this. And for the theory of the defined by topological recursion, we may need more conditions on the curve. Okay, so then we can write down the Virasoro conjecture. So now I have not defined this theorem. I will introduce later, but roughly speaking, the Virasoro conjecture is consists of some set of differential operators which kill the descendant partition function for this coil T. And as introduced in Chauvelin-Kopke, already introduced the Grom-Witten case, but for other cases, just similar. Just we replace those data in the LM to the one that we used for the given theory. So the Virasoro conjecture, So first, for Brun-Witten type series, the L-1 constraint, also known as the string equation, is proved by Witten, and the L0 constraint first discovered by Horry is equivalent to the can be deduced from the homogeneous property and the delta equation. And for Brun-Witten theory of a point, this is equivalent to the Witten-Casares theorem as mentioned also in Chauvel's talk. And for genus 0 case, it was proved first by Chauvel and Gantier, and then later by Dubrun, Zhang, and Gessler. So for the genus 1, the genus 2 case, under some conditions, I think also was introduced in Bill's talk, Liu proved it's the genus 1, genus 2, so also Dubrun, Zhang proved it for the semi-simple case. And then later, so for general genus case, it was proved by Givento and Telemann. For general semi-simple, for cooperative with general semi-simple from his method. And then for Brun-Witten theory of curves, it was proved for all genus by Alkenkopf and Panda. And recently we have a work in progress to prove the genus 1 versor for the Brun theory of the continuous intersections in projective spaces. Okay. So in this talk, our major goal is not just not to prove the versor constraint for some theory. We just want to explore the effectiveness of the versor constraint, and also we want to see what the versor constraint can tell us in computation. So our observation is that first in many years ago, the 2003. Gassman has a paper which says that you can use versor past Broglie recursion relation to deduce all the Brun-Witten invariants of Pn. He has some computer program to do this, written by C++. And then also in 2019, Jian Zhou and Qingsheng Zhang, they have results say that if you consider the Brun-Witten theory of point, what we call the Witten theory, and the versor plus some change of coordinate will give you some polynomial solution. So this was conjectured by these two physicists. And so then
Sorry, whether versor and topological recursion are independent?
I'm not. They are not totally independent. They are dependent. But if we consider Broglie recursion, then we can use not all but part of their sort to solve it.
Whether topological recursion is not sufficient to compute all the.
Sure. The topological recursion relation is not enough. Yes. Okay. So our idea is that okay. So we think this Gassman's result can be seen as that we can solve the ancestor version of the versor constraint, because the ancestor and descendant correspondence in fact is proved by using this topological recursion relation. So that's our motivation, that we want to introduce the so-called the ancestor versor conjecture. Also, for semi-simple case, that the ancestor versor constraint will gives a very effective algorithm to solve the generating series, and we solve it just in terms of polynomials.
What do you mean by polynomial solution for consensuated case?
Oh, this means that if we, because you know the consequence or here in general the polynomial structure means that so first the Brun-Witten invariant is generating series of infinite variables and of infinite terms, but we can find some genus 1 generating series, and we can rewrite the FG in terms of this series, generating series. This we call it some generators or something, and then it becomes a polynomial. And also in this talk, I want to discuss the case where there's no flat unit, because there's many series we are interested has no flat unit, and we also need to consider the generalized Virasoro. In that case, the Virasoro will not start from L-1, but maybe start from some L-M0, so positive M0. Okay. So now we introduce the definition of the Virasoro operator. So the Virasoro operator, as I mentioned, it just consists of very simple data. So the first data is the grading operator mu. So the mu is just as I mentioned in Gromita series, just the degree of the class. So in FGRW series, also the degree of the class. So the operator rho is the first chain class in Gromita. So these two operators are basic data for this Virasoro operator. And with these two basic data, we can define this Virasoro operator. It looks complicated, but I will show you it's quite simple, in fact. Rho is the multiplication by the first chain. So we can use the given total quantization to reformulate the Virasoro operator. So this is the standard quantization of Hamiltonian. So first we consider a vector space V with basis phi e, and then we consider this this formal space which consists of the vector space, some vectors with some powers of z. The powers can be positive or negative. And then we define a symplectic form by using this symmetric two form over V, and then we take the residue, we get the symmetric form omega for any Fg lying in this infinite dimensional vector space. And then we can define the standard quantization by, so first we for operator A, and satisfy this condition, we can define a Hamiltonian HA, and then we define the quantization of this Hamiltonian by just replace this, because it's a quadratic form, so we can just replace these three types of terms by the operator. This is just standard quantization. And then by using this notation, then the Virasoro operators will be simply the quantization of this small Lm plus some additional terms. So this term will just appear in, you see, in as L0 here. So then, in fact, this Virasoro operator will be very simple in this Leventhal quantization formula. And then we want to generalize this operator. So we introduce something we call L top. We simply replace this rho here by this epsilon, this what you call the E. This E is just the quantum of the multiplication by the Euler vector field. So here means that this Lm tau will depend on tau. So here the original Lm is independent of tau. But here we define something dependent on tau. So you can consider it as some Lm on the shifted quantity on some given tau.
Sorry, can you remind what's rho?
Rho is an operator, I mean, for this theory. For example, for Gromita series, just the multiplication by the first chain class.
Okay.
This is given data. So the given data is mu and rho.
Then
But-
multiplication is the real cohomology product.
In the Euler, yes. Not quantum. But here it's quantum. So roughly speaking, in Gromita series, the limit of this guy will recover this guy.
Uh-huh.
When you take call it to 0, it's just the orange one. Okay, so with this this LM tau, we can define the we call ancestor Virasoro operator. So just almost the same. So first we take the quantization here, and then we add some more terms here. Sorry, I think here we should also have. So this term should also only appear for genus 0. I missed something.
Sorry, so the red terms come from cocycle?
You mean this one? Yeah, I don't know. I mean, we just I mean, do computation and to find this. Just do the conjugation of the original one. And then we can reformulate the original Virasoro conjecture in this form. So, mean that so first the original Virasoro conjecture is for the descendant, but now we reformulate for the ancestor. So say that the ancestor potential function the A will satisfy this will be killed by this L tau. So of course it will be equivalent to the original version because the ancestor descendant correspondence are required to be held for our theory, like for Meta theory, actually W theory, and it is proved for this theory. And then yeah, as I mentioned, so assume the genus 0 part of the descendant Virasoro, then the ancestor one will be equivalent to the descendant. So for each m. So here we say for each m because later we will see that that some m will, I mean the m will not start from maximum. Okay, and then there is some result we may use. But this result I just reformulate of the result is here of Liu Tian and Liu's work. But we just think it as some in the language of the ancestor Virasoro. Okay, so for example here the genus 1 part of the ancestor Virasoro constraint, you just directly from that constraint you can deduce this one, and this one appear in Liu's paper in the proof of genus 1 Virasoro. Okay, yeah. So why ancestor? As I explained, so because in Gassman's result, he considered the broad recursion relation, and then this was replaced by the S matrix transformation. So then so here this means that these two are equal up to some unstable data, as I mentioned, it up to the genus 0, 1, 2 point function, and genus 1, 0 point function. And especially there is a special choice of tau. Say that if we pick this tau in satisfy this equation. So in fact, for each big T, we can compute this tau. This tau was called the Dagworth-Witten map. So if we pick the tau to be this tau Dagworth-Witten, then by dimensional reason, the ancestor free energy will just become the polynomial. That's why we get a polynomial recursion, because we pick this special tau. And this ancestor Virasoro equation in this case is equivalent to the Duran-Jones loop equation. Okay, so now we rewrite this ancestor Virasoro equations, and we can see that it can written in a form. So in the left-hand side, it involves the derivative, the linear operators on this Fg. And there is some matrix, the coefficient, we can consider it as a matrix. And then on the right-hand side, it's some lower genus. It is totally determined by the lower genus Fg. So then we can see that if this matrix is invertible, then we can recursively solve this Fg by using lower genus Fg. So as I explained here, so here, this matrix is in fact Oh, S0 is the first ancestor coordinate. It's because we want diagonal weak map that equivalent to reset S0. But this is a vector. This S0 is a vector. I mean, this simply means that after the ancestor descendant correspondence, we have no constant term in the ancestor coordinate. So this is equivalent to say we choose the thought to be the diagonal weak map. And then after choosing this guy, this equation becomes only the first 3t minus 1 times n of them are independent, and then we can write it in matrix form, and we can like I mentioned, we want to solve it if this mg is invertible. Okay, and then we can just compute this determinant of this big matrix. This mg, okay, so I should say more that this mg is something like you can consider it as a restriction of an infinite dimensional matrix. I mean, it will match in the lower terms, and then when g goes larger, and it will goes larger, but the lower terms match. So we can compute the determinant for a fixed g. So it means we have a truncation of this matrix. It becomes a finite rank, and we compute to get this result. So there are some data. These data are all from some genus 0 data. The explicit formula here. So they are just some genus 0 data. So from this formula, we can see that when the for this manifold is semi-simple at this tau, then this determinant will be non-zero. So as I mentioned here, so in this semi-simple case, this matrix, the determinant is non-zero. That means we can just totally solve the systems, and then we can solve it because all the things are just these guys. So we can prove that this Fg are solved by polynomial recursion, and the solution which lies in this polynomial ring. That's why we call it polynomial structure. And here we also use the delta equation. These are some examples. So the first one is, I think this is well known here already, maybe in Dorian John's paper. And then we consider some other examples like grammation of P2. And this result are very long polynomial, but we can check that if you take the expansion of this polynomial, it will match with Gassman's. He has some program and some numbers we can check match with his result. This is the polynomial for the we call three spin theory, or the FRW theory of A2 singularity. Okay. So now I start to consider. I want to generalize the result I introduced to the quality with non-flat unit. There are several motivations. So, for example, so first we can see in the literature that in a model called the authentic front. So this model is in fact can be defined by a QFT, and the Khazar and Zubrov they prove that the generating series satisfy the Virasoro constraint, and the theory can be defined from the topological recursion. And this is a theory without a flat unit. Also, recently the negative R spin theory was defined first by Noberi for R equal to 2, and then defined by these three guys for the R larger than 2. It's just defined by the Kudo class, but because the Kudo class they have some parameters, it takes some. The Kudo class depend on the two parameter s and t. If they take the s equal to -1 and sorry s and r is just this r, then it's just a negative r spin class. So this negative r spin class definition is much easier than the Witten class because it does not involve any virtual class technique. It's just a kind of twisted class. But very interesting is that this negative class R spin theory it also has no unit. So this example cannot be included in the result I have introduced. That's why we consider this. And also, there's many examples in the topological recursion that it has no unit because in the topological recursion there is some. I will not introduce this here, but roughly speaking, it depends on some two functions called x and y. So the y is you can freely choose it to make this theory has no unit. And this topological recursion has been proved to identify with Giventhal theory or identify with the same symbol theory by the authors. One of the authors here. Yeah. So then I will introduce the coefficient with non-flat unit, some axiom. So first, in this case, if the theory has unit, we will have a 1 here. But now this is not 1, but it will be something. In Telemann's paper, it's called the vacuum. So the vacuum is some formal series on Z with vector value.
So this is what happened for the numberless class and the...
Yes, in number class they have that. So this vacuum is studied in Telemann's paper, reconstruction theorem. Also, there will exist Euler vector field, but we need to do some modification of this Euler vector field. So I think this is totally new because I never seen this, and we found that we need to do some modification here. There is some shift here for the original Euler vector field. So just simply shift here.
When we compare with the second term, it just check the R.
Yeah, you can think that, but the difference is that usually the second term only consider the degree 1 term, like the first chain class. But here the shift can be in any degree. Yeah, you are right. You can put it there. And the vacuum vector need to satisfy the homogeneous condition because we need one more condition here because we are sort of always related to the homogeneous quality. We need this. Okay. Then we, as before, so the formula is exactly the same. We can have the generalized analysis of the Rosoro conjecture. The only difference is that here we have some shift by this. Originally the shift is just the delta shift, but now we need to shift by this vacuum vector, this V. So the shift is changed, but all the others are the same.
Yes, the vector, so when you write the vector, the definition for the vacuum.
The vacuum is the basic data in the common field theory. For each theory, we can compute that vacuum. In fact, the vacuum can be computed very simple because you see there is a vacuum equation.
What is psi?
It's a basis for any
Psi.
Psi.
On the top.
Here.
Yes.
Oh, it's just the psi class on the n+1 market.
Yeah, but I don't understand. This is a VI are element in this Frobenius manifold, right?
Yes. Yeah, in fact, you can put this outside here. I mean, this omega only eat vectors, but this V is a formal series. I mean, you just multiply by some cycles. You can put it outside.
Yeah, still, the formula looks very strange because omega takes things, it only takes things from.
Yeah, yes, you are right. But in the literature, start from the Pixon, PPZ, the Pixon independence walking, they use this notation. All the papers use this notation. You are right. This omega has no operation on this side. But in the literature, they always put it here. You can put it outside, but because this V is, a formal series, so you have to put it here.
Yeah, but also there's another interesting, does this vacuum depends on the choice of V1 to Vn? In principle.
Not depend. The V is a fixed vector. It is.
V is not fixed. It's any element in.
Not element. I will explain you. So here, by using this equation, you can compute this V by using 1. Because this will, you can look at the power expansion of Z, and you can look at the expansion. This will give you a recursive formula for this V, the coefficient of each V. And you can compute it by just using the unit, the non-flat unit of the quantum product. So the V can be computed. Okay, so here this is the shift, but the versor are the same. Okay. So as I mentioned, so the genus 0 ancestor versor always true, and the genus 1 versor are equivalent to the here. There's some difference from the one with flat unit. We have one more term. And of course, for semi-simple theory, one can prove that this always hold. Okay, then we introduce the descendant version, the generalized versor. So the descendant version is very different from the ancestor version because the ancestor version always starts from -1, m larger than -1. But for the descendant version, it cannot be that case because for some reason we will need some integer we call m0 that the versor start from some m0, and also we need to add some constant for this m. In fact, the constant not for all the m, but only for part of m. We'll explain later. And also there will be a shift by this Q, but the shift is no longer the vacuum vector because the vacuum vector is for the axis, it's in the curve T. This will be some descendant shift, and there are relations between them. You can compute it and probably.
And how do you choose this M0?
Yeah, I will explain. I will explain later. So, okay, so this result also we have introduced. So assume the genus 0 part of the LM constraint, then the ancestor LM will be equivalent to the descendant LM. So the point is, so you see, so the ancestor always holds for the semi-simple case. The ancestor always holds for the m larger than -1, but the descendant, as I mentioned, is might not. So where it fails, it just fails in the genus 0. So once we have the genus 0 LM constraint, then for when the ancestor holds, then the descendant will hold. So the point becomes we consider the genus 0. Yeah, here I mentioned that for the semi-simple case that the ancestor will always hold. And this can be proved by the relations. In fact, by using the same technique of Gillenthal, he proved that the conjugation of L with R and T are equal to the of the Pacific Witten LM will be equal to the one defined in the beginning. The Arlington norm also have a version of the Manchester-Russell constraint. He just defined by the conjugation of LM by the T and R action. So he do not need the homogeneous property. But if it is homogeneous, as I mentioned, so by using Gibbons formula, we can prove that that one is the same as ours, Russell operator. Okay, so now we see that for this this non-flat unit case, the point is when for the same signal case, when this LM constraint holds for genus 0 part. Let's recall the proof of the original genus 0 descendant Russell conjecture. So this picture is I think it's from Giventhal and based on the proof of Liu Tian and the Dobrin Zhang's proof of the genus 0 Russell conjecture. So first, the string equation is just gives the L-1 constraint. As I mentioned, the dilatant path homogeneous property gives the L0 constraint. And then together with topological recursion relation, one can get the LM constraint. For the non-flat unit case, so first the homogeneous condition is we still require it. And we still have topological recursion relation. But the string dilatant equation no longer holds in general. Okay, so then we find that there are two situations that this can be held. So the first case is when the string equation holds. Then as the original proof, we can prove that the LM will hold for all the m larger than -1. So this, of course, this will include the case with unit. But the second case is interesting. So this case is say that so the string equation might not hold, but when the conformal dimension, this delta is equal to 2 times m0 plus 3. So m0 is some positive, so non-negative integer. And then one can prove that the LM constraint holds for this m larger than m0.
And so this delta, you define it through the Euler vector field, right?
The delta is not from the Euler vector field, it's from the homogeneity of the coeft. So it's a basic, it is called the conformal dimension, it is a basic number for this series. You can for any you give me your theory, you can compute it. For example, for Gromit theory, this is just the dimension of the target, right?
But this conformal dimension can be rational, right?
We do not consider, I mean, in that case, we only consider there is an integer such that this code. So in fact, we only consider the number is an odd integer. That's how should do that.
Minus, plus minus.
Okay,
No, I think it crashed. Yeah.
Refresh maybe. I think it should be so fast. Okay, here. Okay, we are here. Great. So you see, we only consider the when the delta is odd. Okay. Because other cases there will be no real. I mean, if the series has no unit, there's no real. Oh, okay. So a corollary is just as mentioned. When this condition holds, then the descendant vector will hold for the m larger than m0. Okay, I think I give some examples, it will be clear. So the first example is I mentioned this prosthetic baton. So in this case, so we can write down all the data explicitly. There is something interesting I should mention, that this row you can see it is as this form. If you consider the Euler vector field, then the row will have no contribution, because the row acting on the unit vector 1 will get 0. It will not appear in the Euler vector field, but the row does exist. It will be important in the Virasoro operator. And we can compute the quantum product. And here, note that there will be a shift. So this shift is, as I mentioned, because this has no unit, this will, we must have this shift in the tau 0 by this 1 over s. S is a parameter which you remember the degree. Okay. Okay, then in this case, using that data, we can define a homogeneous curve T, and then we can define the Virasoro, because we already have this data. As I mentioned, the Virasoro is just defined by this data. And the only difference is that here the shift is no longer the Dilaton shift, but shifted in the, you see, the Dilaton shift is shifted by z, but here is something independent of z. And also we need some, so in this case, the conformal dimension is, like as I mentioned, is 3. So that means m0 is equal to 0. So for the Virasoro,
What is this little s?
little s is some parameter. In fact, you can set it to be 1. It's just, defined in the theory. We just, because we use the notation of this Khazarian Zagreb, and they have some s in their setting.
Sir, and why is this extended descendant form?
Oh, it's why we call this extended, because in their paper they consider in fact they consider a one-dimensional restriction of the full theory. It's like they only have one. Okay, you just look at here. So we can restrict the descendant variable. We have two types of. We have two T1k and T0k. And when we take T0k to be this k times k minus 1 plus 1, and we take T1k to be all 0, only except for the first one, means the non-descendant, the primary one. And we take this parameter initial equal to u minus v over 2. This is just some number appearing in their paper. And then we can this potential function will recover their one. And they have a Virasoro constraint here. But you see, they only have this pj of this corresponding to some multiplied by some factorial of k and by this tk0. But we still have tk1. By Givento's definition, we will have a Virasoro operator more than this guy. We will have some other terms. And then. So by our result, we can recover their Virasoro constraints when we restrict to this direction. That's why we call this extended prosthetic descendant form. I don't know how it's called, because I don't see the theory describe this full theory. Yeah, so it's just an extension of the original one. So this is the first example, and we can see that this has conformal dimension delta equals 3. So we have with the Virasoro will start from L0. Okay. The last example is what we call the negative R-spin theory, the deformed negative R-spin theory. Deformed is just they have a parameter called issue. that can be appear in the definition when you use the pseudo class, you use the shifted pseudo class. Okay, so then the data is like here. So we have some shift in the Euler vector field, and yeah, here you can see the shift will be just the shift by the last vector, this phi r minus 1. And then we will have a C0, which is non-zero. All the others are zero, are the same as the original LK, but the first one is non-zero. And then use this data, we can recover the Virasoro constraint for this negative R spin. I did not know this. So this is the basic data. We have the state space is a dimension of R minus 1, and this is symmetric linear form, and this mu and the rho, we all have them in the quantum product. Yeah, and as I remark here, so when this R equal to 2, this Virasoro is known is that the Virasoro constraint for the generalized BGW continuum function, and we just take some simple change of variable. We can recover this one. So this one is appearing like Alexander's paper. So here we generalize to the all the R spin, negative R spin case, but we see that here the conformal dimension is also delta equal to 3. So in this case, the M0 is also equal to 0. That means we start from M0. This match with this case. And I didn't see, I mean, in the literature, an example that this delta is equal to like 5 or something to make the M is not 0, but M0 is 1 or more. I didn't see such an example, but we constructed such an example, but I didn't see that in the literature. So I don't know if there's some interesting example that has generalized other generalized Virasoro.
And you constructed one example for which gives which kind of which M0?
M0 equal to 1.
To
so
1.
that means the Virasoro constraint starts from L2.
Okay.
Yeah. In fact, we construct that example is motivated by it's motivated by the student of Jian Zhou. Her thesis is about some matrix model, and she considered some matrix model that satisfy a Virasoro constraint starts from L2. But then we checked that her example is not a QFT, so we made some modification of her example, and to make it QFT, then we get that model. I think that our model is very close to hers, but not totally the same, because it's not QFT, you cannot use it.
Mm-hmm.
But I think anyway it should relate it to some matrix model. We just not write it down. Okay, I think I will stop here. Thank you.
Any questions, please?
So I'm a bit confused with all the hypotheses, but the way to compute the invariance from Virasoro, you can do it for which kind of conjugate field theory? So you said like you can
Semi-simple.
Semi-simple.
Yeah, semi-simple. We have a polynomial recursion. Like here. Like we solve. Yeah, we would have a big matrix MG, and we solve it. We can have a
Okay.
recursive.
And that's okay. Do you get some explicit formula then, or it's just
We just try it in the. In this case, we also tried in the case like the plan I mentioned or negative R spin, but I didn't present it here.
Okay.
Can you present as a vector of line? I think polynomial recursion. Well, what do you mean by that?
Polynomial recursion means that so first it is a recursion because when the M is invertible. So
This just shows the determinant f itself is
this shows this determinant is non-zero, so we can always solve this equation.
yeah, but when you solve it, those things in the determinant will go to the numerator denominator.
Yeah, you are right. So here you see the determinant has consider of the x, y, z, and the polynomial here always consider x minus 1, y minus 1, and z minus 1. Simply is this reason. So you can see in the example, so you will have something, this is something related to x, and also you will have something here. This is related to x, y, z. Because
What is this epsilon alpha?
this is just the quantum product by E, and you take all the entries of it. All the entries of the quantum product.
Excuse me, could you please go to the last slide?
The last page?
To the last page, yes. Okay, so here the negative R spin theory. Is it the same one which is considered in the paper you referred to at the beginning?
Yeah, exactly the same. Yes.
Exactly the same.
Yes.
Thank you.
More questions? If no questions, then let's thank again. We have a 20-minute coffee break. I think this way.
Давайте я настрою сейчас. Можно только флешку?
А мы на рабочем столе до этого доклада.
На рабочем столе вот.
Вы знаете, ну, смотрите, микрофон.
Да, но чувствительно, может там настроишь Windows.
Если честно, я не знаю, если такая своя система. Знаете, что можно сделать? Можно просто, чтобы вы слайд ставили тут, да, вы, как я понимаю, ничего не писали, да? Просто поставили. Просто если ставите больше слова, то будете ставить прямо микрофон.
Еще раз сказали, что плохо видно. С камеры хотите давать из самого экрана?
Сейчас вы представляете, что не будет, мало ли, да. Тогда давайте я просто сюда поставлю слайды, угол камеры, чтобы он показывал.
Почему не
В центре лучше.
трансферировать непосредственно экран?
Ну, не экран, но...
Мне кажется, так лучше выглядит.
Не, ну ладно, если так... Не, так, конечно... Просто для фальши.
Ну да, но там просто жаловались, что второго склада уже брать не
But I can send you
Можно, в принципе, зум запустить. А Саша ушел. Мы не знаем, логин пароля.
Вот тут в уголке. Как раз.
Да, главный вход вы увидите, там большое здание.
Можно сделать так.
Я фотографию
Но внутри
Ну, в общем, мне кажется, что это
Так, break, please.
Ну, какие мероприятия? Все надеются, что мы отпишем.
Так, на камеру, да, с камерой.
Я думаю, что здесь больше никого не будет.
Или то другое, или только...
Let's go to have a break up to the end. And